All right, so today we're going to talk about 9.2, which is estimating the sample mean. So the sample mean, remember, refers to the random variable x bar. We talked about this in chapter 8. It was the first one to come up. And the idea is maybe we would want to use this if we wanted to estimate some sort of parameter like this, mu, where mu is maybe like the average number of dogs in a household in the US. So keep in mind, again, mu is something that exists. It's real, it's out there, it's an actual parameter. But at the same time, we would have to interview every household in the US in order to get it. So maybe instead what you do is you go and you collect a bunch of data, you interview so many households. So let's say we have some sort of data that's presented like this. This represents a bunch of households that you've interviewed. And so since there's 16 data points, you've interviewed 16 households. And what we do is we might choose that to guess what this is. And we would compute the mean, and that's perfectly fine. And you can sum up all the data points. So these are all your xi, sum them up, and you divide by the number that you worked out. And if you did that with these, you would get 1.563, about like that. So you could, estimate that the average number of dogs in a household in the United States is about 1.6 or 563. Now, you might be wondering, in the same way of population parameters, how good of an estimate is this? And in a sense, it's not a very good estimate if we're trying to take this and actually guess what this is. Because we know that this point estimate is never going to actually be this value here. Because again, this is continuous, and so it can take any possible number of values. In fact, this is a much bigger thing than a proportion, because this is what we're doing here is we're allowing any number of dogs. Well, any positive number of dogs. It wouldn't make sense to have, -1 dogs as the average number. So any positive number could be that. And so this thing, again, the possibilities are infinite and it's continuous. And so trying to say that this is the actual number makes things pretty impossible. So what we're going to do is we're going to find a range of values. And we're going to take that range and we're going to figure out the distribution. So things actually work out very similar, and we'll get to that way, but they get a little different, and it gets a little confusing at first, but just bear with me. Okay, so I'm going to stop you before you go any further. If you haven't worked on the problems from the previous section, if you haven't started that homework, you're not going to want to go further with these videos because it's going to seem very, very confusing. You're not going to get a sense of what's actually going on. So really go back to that video, check it out again, make sure you really get what the idea of confidence interval is, do some of the problems, work those out, and then come back to this video because this just ramps up the stuff that we were kind of talking about before. So what we want to do is we want to find a confidence interval for x bar. So like a confidence interval for our parameter. So remember that if we look at the distribution of x bar, it's going to be normally, well, it's not going to be normally distributed necessarily, But if we choose our sample sizes large enough, if we choose them to be 30 or more, we can assume that it's normally distributed. And this doesn't matter what the distribution of the underlying data is, it's going to be normally distributed. Another thing we can also assume is that if your underlying data is normally distributed, that X bar will be normally distributed no matter what n is, no matter what the sample size is. So what we're working with here is, remember that regardless of the distribution of X bar, we have that the mean is always going to be the mean of the underlying data. So this is mean of underlying data. And this is what we want to guess. This is what we're trying to approximate. Remember, so you can think of this mu as the actual parameter of dogs, or of number of dogs in a household in the US. And this is going to be your guess, and your guess can kind of shift around to the mean, around the actual parameter that we're trying to guess. So one thing you might try to do is you might try to construct your confidence interval in the same way that we did before for a proportion. And you would get something like this. You would normalize it. And what we would do is we would just kind of figure out what's happening here. Actually, what I'm going to do is I'm going to match this picture. Your confidence is going to be the area that's shaded. And so you would get these different values, and what you would find is you would find that, that the error term that you want, that E, is going to be Z alpha over 2 times standard deviation. But this time, it's not the standard deviation of a proportion, it's the standard deviation of X bar. So now you have to remember, what is the standard deviation of X bar? Well, that's going to be standard deviation of your underlying data over square root of the sample size. Now here's where the problem lies, and this is where things get weird. We don't know what this is. This is dependent on knowing the underlying data. We don't know that. So you might think, well, let's replace this expression with this thing here, where this S is the sample standard deviation. All right, we can try that, but remember, how you compute this is by summing up the, all the data minus the mean, and then you divide by n. But the sample standard deviation, sum up all the data minus sample mean, looks the same so far, but then you divide by n minus 1. This is where things get thrown off because of that. So this term here doesn't work. And I guess what I'm trying to say is, if you were to take this and you were to translate this, try to standardize this with the variable X bar minus the mean over, instead of using the standard deviation, you use S over n, then what this becomes is this is no longer normal. When you use that. And this is a little bit beyond the scope of the class, but this becomes its own distribution. And there's a lot of things about this distribution that are nice. This is called a t-distribution. It's still going to be symmetric. It's still going to have mean 0. It's still going to be able to be useful, but we have to remember it's not going to be exactly normal. It's not going to be the same thing as the z distribution, which will be normal. So we'll go over some characteristics of it. Okay, so this is the picture of t-distributions. On top we have a normal distribution. Then after that, the green one is going to be when we're using a sample size of n. And notice it's a little bit lower than that. And then for the other one, we're using a sample size of m. And that t-distribution is a little bit lower than both of them. And what this is going to mean is that your sample size is going to be a little bit less the lower you use. And another way to think about that is the smaller sample size you use, it's going to kind of be flatter and be more spread out. So your standard deviation is going to be a little bit bigger. That's the sample standard deviation, keep that in mind. And then what's going to happen to keep in mind is that as your n increases, it's actually going to get closer and closer to being normal. So these are just some properties that you want to keep in mind. And I'm going to write them down here. So these are going to be different distributions for different sample sizes. And if you look in the book, it's going to say degrees of freedom. And we'll talk about the connection between the sample size and the degrees of freedom, but just keep that in mind that if you're changing the sample size, you're changing the degrees of freedom, whatever that means. In this case, it's just going to be one smaller than the sample size. That's what the degrees of freedom will be. The other one is going to be t-distributions are centered at 0. They're also going to be symmetric. About 0. That means you have symmetry. So in those ways, it's like a normal distribution. So this is 0.1, 0.2, 0.3, 0.4 will be area under curve is 1. So again, very similar to the normal distribution. However, if it was truly normal, it would be the normal distribution with these properties. So the fact that we know it's a little bit different, that it looks different, tells us it can't be a normal distribution. It doesn't actually follow the normal distribution. It's a little bit kind of flatter, or yeah, I guess that's what it is. It's kind of a little bit flatter and more spread out. And then 5 is going to be as n increases, t distribution becomes more normal. Okay, so again, that's kind of the picture you have here. As we increase the sample size, it's going to start kind of closing in on being normal. This is going to get closer and closer to the norm, and this is going to go up a little bit more. Okay, another way of rephrasing 5 is it's the law of large numbers. So as you increase n, as you increase your sample size, things are going to get more normal. Things are going to be easier to find. Okay, so now we want to start computing confidence intervals with t-distribution for the sample mean, for x bar. So the idea is we're given a sample size n, so that's the n we're working with, and our confidence is c times 100, where c is going to be equal to 1 minus alpha. Again, this is very, very similar to what we were working with when we were working with proportions. Well, then, our confidence interval will be, it'll look like this. It's an interval where you have x bar here, and you have x bar minus alpha, minus e, x bar plus e, where e is going to equal t sub alpha over 2 times s over the square root of n, where and if so t alpha sub 2 is the critical value with degree of freedom n minus 1. And so degree of freedom we're going to shorten by df. And it's going to be n minus 1. So remember I mentioned they're going to talk about degree of freedom, and that's just going to be 1 less than your sample size. And so I'm going to point out you find this on table 7 in the back of the book. And the picture is, again, it's just going to look like this. It's going to look like a normal distribution, but keep in mind it's not the same thing. It just shares a lot of properties with a normal distribution. And the notation t sub whatever that value is, it just means that the area to the right of t has to be alpha over 2, or has to be whatever that value is. So again, you can find this stuff on table 7, and we're going to do that. One thing I want to warn you about, only use this when the distribution of x bar is normal. So we're going to talk about that in a second. So only when normally distributed. And so what can we do to figure that out? Well, we have to make sure that the sample data is random. It's randomly chosen. We want to make sure that it's less than 5% of the population size. And we have to either make sure that the sample data is at least 30 or that the underlying data is normal already or normally distributed already. Because if it is, then we can assume the sample mean is normally distributed. If it's not, we have to make sure that the sample size is large enough to get the central limit theorem to kick in. And if it is, great, we can just use that. So keep that in mind. Only use this when X bar is normally distributed. There's ways around it if it's not. We can still kind of use different things, but that would be discussed in a different class. Okay, so what we're doing here is we're back to this question about number of dogs in a household, the average number of dogs, and we're going to be told to assume that it's normally distributed. So we have that our underlying data is normally distributed. That's an important assumption, because notice that our sample size is only 16. So we'll talk about that in a second, but to the left, we have our sample of 16 households. We're going to assume that this is random. And then what we're asked to do is A, find T 0.025 using table 7. And then B is compute the 95% confidence interval of this data. Okay, so let's answer A first. So because this is related to this question, remember our T distribution relies on our sample size. Our sample size is 16, and that means our degrees of freedom are going to be 16 minus 1, or 15. And so if you go to table 7 in the back of the book, and you look at it, it's going to say, like, it's going to have a column of degrees of freedom, and then to the right of that, you're going to see a bunch of numbers, and these are going to be the critical values. Or these are actually going to be the alpha numbers. So these are your kind of values. So these are alpha if we're talking about T sub alpha. And then underneath all of those, you're going to get, well, you're going to have your degrees of freedom, and our degrees are all the way out to 15. And then, you know, you're going to get so many things here. But what we want to do is we want to focus on the row 15, because this is our degrees of freedom. And then from there, you want to focus on the column of the alpha that you're working with. Okay, so we take this alpha, and again, what this means is here we have our T distribution, for our degrees of freedom equaling 15. And this area here is going to be the area to the right of the curve, or right of the value. And the value here is going to be your T value. And so what you're going to get is your T value is 2.131. And that's the value, we're going to use it later, but that's your T value. Okay, so the next part of the question says, compute the 95% confidence interval of this data. So if you run this data through your calculator, you can find that X bar is going to be 63, and the sample standard deviation is going to be 0.892. And then our confidence, remember we wanted that C times 100, we want this to be 95. And so C is going to be 0.95. And if C is 0.95, then C has to be equal to 1 minus alpha, which tells you that alpha has to be 0.05. It's the complement of C. And now we want our confidence interval to be something that looks like this. Well, it's going to be x bar minus some error term, x bar plus some error term, and the error term, remember, it's going to be the t value that you're working with, sub alpha divided by 2, times sample standard deviation divided by the sorry, there's a car alarm going on outside. One second. All right, the car alarm is off. Crisis averted. All right, so what we're working on here is, remember the error term, it's going to be your t value, your critical value here, where the alpha we're using is 0.05, and we're dividing that by 2. So this is going to be t sub, what's 0.05 divided by 2? 0.025. And our sample standard deviation divided by square root of n. All right, well, we just so happen to find what that t value is. It's 2.131. So what we get is we get that our error is going to be 2.131 times the sample standard deviation divided by the square root of our sample size. Well, we have 0.892 divided by the square root of 16. And remember, the square root of 16 is just 4. So if we run those numbers through our calculator, you get that this is about 0.443. And that's the error. And so if you compute this, remember we have our sample mean and our error terms. You're going to get a confidence interval of about 1.09 to 2.04. And again, what this means is that we're 95% confident that our methods work, and we were able to capture the actual mean as a number between 1.09 and 2.04. So we're 95% sure that our methods worked and that the average number of dogs that a household has in the United States is somewhere between these two numbers. All right, the last thing we want to talk about is let's determine our sample size if we want a specific error. So the idea is, consider that we're fixing an error that we want, and we want to use a previous data for our standard deviation. So that's the setup we're doing. So what we know is we know this E, we know this S. And technically, all the critical values of t are known. And so all the thing that we need to work out is n. That's the only kind of variable thing. So what we're going to do is we're going to solve for n. And how we're going to do that is I'm just going to flip everything and get the square root of n divided by t alpha sub 2 times, or t sub alpha divided by 2 times s equals 1 over e. Then I'm going to cross multiply, get square root of n has to be t sub alpha divided by 2 times s over e. And now I'm going to square both sides and get n equals this thing here squared. And this is a perfectly fine formula. Makes sense, except for one piece of information. Yes, we've fixed our error. We've chosen the error that we want. And we are using previous data for the s. But remember, the t distributions depend on the n. The t distribution that we're using depends on that choice of n. And if we haven't chosen n, we don't actually know which t distribution we're using. Even though all the t distributions, all those terms are worked out, we can find those things if you pick an n. So what we're going to do is we're going to say, well, remember the t distributions, they approach the normal distribution as n gets large enough. And this is kind of the idea, is we usually want to fix an error so that it's small enough. And so you're going to have to increase your n. So if you want a smaller error, you're going to have to pick larger and larger n. So if we're picking larger and larger n, and we're getting smaller and smaller error, then our t distributions are going to get closer and closer to z. And so what we're going to do is we're going to choose our n based on the idea of the z choices. So you pick your n based on this formula. So S is again sample standard deviation from previous data. E is the error you want. And then you go and you find your critical values from the normal z distribution. And then you square that once you throw it into this. So you multiply the s and the z together, divide by e, you square that, you get an n. And since n is a sample size, you're not going to be using half values or anything like that. So you always round up. And it's important that you round up, because if we're being precise about things, if you round down ever, then that's not going to necessarily give you the correct error. If you round down, then your error is actually possibly going to be greater than what you want. So you always want to round up, because higher n is always going to correspond to lower error.